Okay, excuse me. Welcome back. So, what a week, huh? We've just barely gotten over the first exam, and your second exam starts on Wednesday. So, what we're going to do today is finish all of chapter 19, and we'll do part of chapter 20. There's more we could delve into in chapter 19, but the basic concepts are pretty simple, and I want time for the more in-depth synthesis stuff that you'll get in chapter 20. So we're leaving behind alpha carbons and carbonyl carbons in this section, and we're going to start talking about benzene rings. And hopefully this will unlock a little bit of mystery to you, because there have been a lot of things we've done before in this class with pi bonds as nucleophiles that for some inexplicable reason we've never done with benzene. For example, you can do electrophilic addition of HBr to a pi bond, and the Br ends up on the more substituted carbon. You do this with benzene, which likewise has pi bonds, and everything just sort of sits there and stares at you and nothing happens. And so far, maybe you've noticed that, maybe you haven't. Maybe if you noticed it, you're like, okay, well, I just need to memorize that nothing happens to benzene rings. Not quite. There are some things that can happen to benzene rings, but molecules like benzene have a special kind of stability that in chemistry we called aromaticity, and molecules like benzene are called aromatic molecules. So benzene is an example of an aromatic hydrocarbon. Sometimes people call this an arene, in the same way that you might call this here an alkene. Not sure with the air quotes. Maybe my Aunt Dinah is influencing my thoughts at this point. I don't know. Anyway, aromaticity, a special kind of stability enjoyed by molecules like benzene. The word aromatic, of course, has other uses. Something that you can smell, an aroma, but actually, and benzene does have a characteristic smell, and a lot of aromatic compounds do, but we no longer use the term at all to refer to how molecules smell. We have better ways of analyzing molecules now than just smelling them. So it's kind of an old historic term, but now we use the term aromaticity to describe molecules that are more stable than expected, even for a conjugated alkene. You're comfortable with the idea that conjugation or resonance is a stabilizing effect. Delocalization of electrons is stabilizing. That's a 351 concept, and really derives from the Schrodinger equation. Molecules that are spread out, atoms, nope, scratch that, electrons that are spread out have lower kinetic energy. But in aromatic, and so you're comfortable with the idea that resonance stabilizes alkenes, but aromatic molecules are even more stable than you would expect for a corresponding conjugated alkene. And we'll talk about that and where that comes from. But for now, being able to identify molecules that benefit from aromaticity is important. And there are three sort of key determining features. First, they have to be cyclic. Second, they have to be fully conjugated. And there's a couple of things that go into being fully conjugated. What do we mean by fully conjugated? Each atom in the ring has a p orbital that lines up with all the other p orbitals in the ring. And we'll see when that happens, those p orbitals mix together to make a conjugated system of pi orbitals, and we'll talk about those in a little bit. But a key feature of aromaticity is that each and every atom on the ring has to have a p orbital that can line up with all the other p orbitals on the ring. For benzene, you can tell that's true. We could draw each of those p orbitals. Each atom in benzene is sp, each carbon atom in benzene is sp2 hybridized, trigonal planar, and on each benzene atom is a p orbital. I'm drawing the top lobe of the p orbitals on each of these atoms, and of course there's another lobe below the plane of the page, 6 of them, all lined up together on adjacent atoms, side by side, basically pi-type overlap. And this is one of the requirements for aromaticity. If one of those atoms was sp3 hybridized without a p orbital, couldn't be conjugated, couldn't be aromatic, couldn't be fully conjugated. Another feature or perhaps consequence or property of rings that are fully conjugated is that they are planar. We'll come back to this a few times, but we'll see that being planar is a requirement and or consequence for being fully conjugated. The fact that the benzene ring is planar means that all of these p orbitals are perpendicular to each of the carbon, carbon, and carbon hydrogen sigma bonds in the ring, and that property makes all of the p orbitals parallel to each other, for which is perfect for side-by-side pi-type overlap. Okay, and then finally, the last aspect is you have to have the right number of electrons involved in that system of pi orbitals. So what I'm telling you is we mix these whatever number of p orbitals together and we get the same number of pi molecular orbitals out. And those pi molecular orbitals are going to be filled by what I'm going to call pi electrons. Those are electrons involved in the conjugated pi bonds of the ring. And we have to have, it turns out, to enjoy the special stability associated with aromaticity, we have to have the right number of electrons. What do we mean by the right number of electrons? Well, the right number of electrons actually comes out of the arrangement of these pi orbitals in energy. But just empirically, even before people understood that, they were able to tell that some number of pi electrons led to molecules that were aromatic, and a different number of pi electrons led to molecules that were actually especially unstable. So I don't know if you remember back in junior high or high school dealing with mathematical series of numbers and how that's sometimes expressed. If you look 2, 6, 10, 14, 18, what do they all have in common? They sort of follow this pattern of what's called 4n plus 2, where people get confused about what n means. It's just an integer. This is a mathematical series. N is 0, 1, 2, and so on. These are the allowed number of electrons that lead to aromaticity. And this 4n plus 2 rule is sometimes, man, we got quotes everywhere today, and an umlaut. It's called the Huckel rule. And I'll show you where that comes from. As I said, it comes from the arrangement of the pi molecular orbitals in energy. But this is basically all you need to determine whether a molecule is going to be aromatic or not. Generally, you're going to focus on cyclic, fully conjugated, and right number of pi electrons. This requirement that the ring be planar is a true requirement. It's not necessarily that useful as a decision point. In other words, you're not really, with one exception in the textbook, and I can't actually think of any other examples off the top of my head besides that exception in the textbook. You're not going to find a molecule that checks all the other boxes but miraculously isn't planar and therefore it's not aromatic. With one exception in the textbook and perhaps some other elaborate molecules people build when they're trying to push boundaries and test the limits of various rules. So look for things that are cyclic, fully conjugated, and have the right number of electrons. Again, with exceptions to not frequent enough to really worry about. If you check these boxes, generally the planar thing will take care of itself. All right, so the best way to do this is just to dive in and do examples. So benzene is obviously aromatic. Here's a boring example. Cyclohexadiene is not aromatic. Why is it not aromatic? Not fully conjugated, right? 2 sp3 atoms in the ring. You need a complete contiguous array of p orbitals on that ring, and 2 of the atoms in the ring don't have it, so this is just flat out not aromatic. Okay. Cyclobutadiene. It is cyclic, it's fully conjugated, but it's got 4 pi electrons instead of 2 or 6. So this breaks the Huckel rule. We're going to see actually that if you have 4 or 8 or 12 or 16 pi electrons, that is, if you follow the pattern 4n, where n is an integer, actually now you experience special instability that's called anti-aromaticity. We will talk about that as well. So again, cyclobutadiene checks the cyclic and fully conjugated box. However, it has the wrong number of pi electrons, and so it is actually anti-aromatic. That means it's especially unstable, more unstable than you would expect for a cyclic conjugated hydrocarbon. The concept of anti-aromaticity is a really interesting one. We won't say too much about it, though I will say that molecules that are anti-aromatic will sometimes distort themselves out of planarity or out of full conjugation in order to disrupt this instability. So people have done cyclobutadiene is sort of a holy grail among physical organic chemists because it's so unstable you can't really observe it except unless you go to really, really, really cold conditions. So you can actually isolate it in a solid matrix of argon atoms at 4 Kelvin, just 4 degrees from absolute zero, and then you can observe it. But at room temperature, of course, you can't. And there's evidence that the 2 pi bonds on cyclobutadiene actually twist a little bit out of conjugation and maybe pull apart a little bit so that the overlap between adjacent p orbitals is not as good. And that actually breaks up the anti-aromaticity and allows it to be not so, still quite unstable, but not as crazy unstable as it used to be. So just as we have this concept of aromaticity, if you follow the 4n rule instead of the 4n plus 2 rule, then you are anti-aromatic, and that's especially unstable. So you can expect questions where, and then you'll find this in your text, on the study guide, on the practice exam. Is it anti-aromatic? Is it aromatic, or is it just plain old not aromatic? And you can see the difference. The molecule that's not fully conjugated is not aromatic. whereas the molecule that's cyclic, fully conjugated, but has the wrong number of pi electrons is anti-aromatic. All right, questions about that? Yeah?
Couldn't you say that the one on the left is also not aromatic because it only has 4 pi electrons? Is that wrong?
Could you say it's not aromatic because it only has 4 pi electrons? It turns out if you're not cyclic or fully conjugated, the number of pi electrons doesn't matter.
Oh, okay.
Yep. So it's sort of that's why I put it third, because you got to check boxes 1 and 2 before you even worry about 3. Yeah?
It's probably not really relevant, but like, how does one look at a molecule and be like, oh, that's going to be planar as opposed to that's going to be calm?
How do you look at a molecule and determine whether it's going to be planar or not? You build a model and you do some simulations or calculations. You also do experiments. The example in your text, I hesitate to draw this because I know when I draw stuff, people are like, ooh, that's really important, I should memorize that. Again, this is the one example in your text of a molecule that should otherwise be aromatic but can't because it can't get planar. It looks like it wants to be 2 benzene rings side by side, except, what did I always tell you? Sometimes draw the hydrogens that are implied but not shown. Do you see that there's a hydrogen here and a hydrogen there? Do you see that they're pointing right towards each other? There's going to be a huge steric clash. And the only way to accommodate that is for the ring to twist itself out of planarity. I'm betting, we're just going to see if Spartan has this molecule. My guess is it doesn't, but maybe if it does, it'd be kind of fun. So, oh no, disaster. Oh, clean it up for us, please. Yeah, okay. All right, there it is. Oh, actually, not bad. At least it modeled it for us. Do you see how it's no longer planar? Those 2 hydrogens, one tips up, the other tips down. It's the only thing it can do. Oh, it's even in the database, yeah. So it can't be planar, and therefore it can't benefit from aromaticity. I'm not going to show you the orbitals, but at least that's the one example of the cases like this. Now, frequently, as I said, molecules that are anti-aromatic will frequently try to tip themselves out of planarity in order to avoid anti-aromaticity. In such cases, it is sufficient, as far as I'm concerned, for you to realize that the molecule would be anti-aromatic. But another classic example of this is the stop sign molecule, cyclooctatetraene, has 8 pi electrons. So it checks the boxes of being cyclic, fully conjugated, but it has 4n equals 8 pi electrons. So it would be anti-aromatic. To avoid that, again, it tips itself out of planarity, and maybe I can illustrate this in Spartan. Let's see, throw the whole thing away. Oops. No. There we go. Cyclooctatetraene, clean that thing up. Do you see it? The 2 flaps on either side actually tip upwards, so now it's not planar anymore. And that breaks some of the conjugation and again prevents anti-aromaticity. So far, it's not at all clear why the 4n pi electrons is bad. The concept actually isn't that hard to get. We'll need to talk about the pi orbitals. But I want to practice the rules a little bit more with a class of aromatic molecules that have heteroatoms in them, and these are called heterocycles. And this is where the wheels start to come off. Heterocycles are sometimes difficult to analyze and determine whether they're aromatic or not. So let's look at this one. This one happens to be called parole. You don't need to know that, but actually this is, there are, of course in every field there's always people that want you to know how smart they are, right? We all fall prey to this a little bit, but we all want to appear smart. One of the ways you can impress your organic chemistry peers is if you know the names of heterocycles. And you see this from time to time as people go, as assistant professors approaching tenure go out and give talks at various institutions. If they've got heterocycles in their talk, by golly, they know what those names are. And some of the names are really kind of exciting, like benzimidazole or oxazolidinone, and if you just rolls off your tongue, it really impresses people. Well, a select group of people. So I doubt any of you will be interested in impressing OChem nerds, but anyway, if you want to, just go look up heterocycle names and you'll see how crazy it gets. Let's talk about parole. Aromatic, not aromatic, or anti-aromatic? Aromatic, that is correct. How did you know that? I only see 4 pi electrons there. What am I missing? The lone pair. Ah, yes, the 2 electrons on the lone pair. Beware, beware, the heteroatom lone pair. Make sure that you know when it can count. Now, notice that this nitrogen is sp2 hybridized. Notice that the sp2 orbitals are taken care of in terms of the 3 sigma bonds, 2 carbon nitrogen sigma bonds, 1 nitrogen hydrogen sigma bond. That means, therefore, that the lone pair can only be in a p orbital. Therefore, it's part of the conjugated pi system. And yes, we have 6 pi electrons. We're cyclic, we're fully conjugated. Parole is aromatic. Okay. Budding confidence, that's great. Let's try something else. I'm struggling to remember the moment in Star Wars where somebody says something confident and then Yoda goes, oh, like big man, let's see what you can do with this one. So, this one is called pyridine. You've seen that one before. What do you make of that one? Aromatic, not aromatic, or anti-aromatic? Okay, I can't tell what you're mumbling because the 2 options, anti-aromatic and aromatic and not aromatic, all end in the same thing. I won't make you raise hands, but you got to be careful with the lone pair. Does it count or not? No, good. Why does it not count? What kind of orbital is that lone pair in? The lone pair is in an sp2 atomic orbital perpendicular to the pi bonds. It's not part of the pi system. It's not part of conjugation. It doesn't count. Okay? Remember that with aromaticity, we're concerned about the number of electrons that are in the conjugated pi system of the ring. Those electrons must be in p orbitals, right? So on each of these carbons, perpendicular to the ring is a p orbital. These 2, we'll just highlight the ones that are part of the pi system. These 2, and these 2. And the ones on the nitrogen are not involved. So, pyridine is definitely aromatic. It has the right number of electrons. Notice also that because this lone pair is not conjugated, it should be relatively high energy. And therefore you would predict that pyridine is a base, that the lone pairs on the nitrogen are basic. Yeah, go ahead, Isaac.
Could you remind me why the nitrogen on the left there is sp2 hybridized?
It looks like it's surrounded by four things. It's sp2 hybridized because the conjugation and the aromaticity pays for that. You might think, because of Vesper, the groups, the two carbons, the hydrogen, and the lone pair should be as far apart as possible, therefore tetrahedral. And that's good reasoning unless you've got conjugation with adjacent pi bonds, which is stabilizing. It spreads out the lone pair, and that pays for the rest of the atoms being, that pays for, not being tetrahedral. Okay, good. We're not done yet. We've got lots of other opportunities. So, sometimes the question gets asked in interesting ways. This one is called imidazole. And there's sort of two questions I want us to answer. Aromatic or not, and then which nitrogen is more basic? So, what do you think? We're cyclic, fully conjugated, both nitrogens are sp2 hybridized. How many pi electrons do we have? 6 or 4 or 8? 6 is the right answer. This one, and there's actually one other one. Which one is it? One on the left. So my grandma always jokes that Grandpa couldn't tell right from left, and she'd have to tell him to throw a rock, Dale. And then because he was right-handed, if he thought about throwing a rock, that's his right hand. My grandpa's a really smart man, but there's some, and I also have a hard time actually on my first shot, right and left, I'll often get wrong. So I don't know what that is, but this one counts, okay? So those are the 6 pi electrons. Why does this one not count? It's sp2, it's in an sp2 orbital, not part of the pi system, and therefore not counting in aromaticity. Okay. So then which of the two nitrogens is more basic? The one on the left or the one on the right? The one on the right is more basic. Right. That's correct. They are not stabilized by, that lone pair is not stabilized by resonance. Meaning if this molecule were to pick up a proton, it would be on this nitrogen, not on that nitrogen. You've actually seen this before multiple times on multiple exams, especially if you've taken a class from me before. This imidazole side chain has a pKa of 6. And what I just drew is the conjugate acid of this ring. And notice it gets protonated on that nitrogen. Okay, so this is worth continuing going on. There's a lot of different things we could do with heterocycles. I'll maybe do one more. Okay, yeah, this one's worth doing. This one's called oxazole because instead of imidazole, one of the nitrogens is replaced with an oxygen. This one's fun because the oxygen has 2 lone pairs. So, how many pi electrons does this molecule have? 1, 2, 3, 4. I've got, do we have 4? Do we have 6, 8, 10? Okay, 6 count. This, and this. Now, the nitrogen we don't need to spend a lot of time on, for the same reasons that the lone pair on that doubly bonded nitrogen doesn't count in imidazole. It also doesn't count in oxazole because it's in an sp2 orbital, not part of the pi system, actually perpendicular to the system of pi orbitals. Let's talk about the oxygen. How come only one counts there? Yeah.
One's in an sp2 hybridized orbital and one's in an unhybridized p.
Okay, so one's in an sp2, the other's in an unhybridized p orbital. Good. The way you reason through that is you say, okay, lone pairs adjacent to pi bonds, one of those lone pairs needs to be in a p orbital, and then you remember what hybridization means, and you also remember that p orbitals are perpendicular to each other. So if one of the lone pairs is in a p orbital, the remaining orbitals have to be perpendicular to that p orbital. That's sort of the definition of sp2 hybridization. The geometry here gives you the idea that that oxygen should be bent, and if you count the lone pair, trigonal planar. This carbon-oxygen bond and this lone pair are all in sp3 orbitals, sp2 orbitals in the plane of the page, and the p orbital is in a lone pair coming above and below the plane of the page. Yeah?
So, is the reason the lone pair on the nitrogen doesn't count is because it's adjacent to another, like, hybridized p?
The reason this lone pair doesn't count is because the p orbital on that nitrogen is already involved in this pi bond. Yeah. Yep. So, for heteroatoms, pay attention. If it's already involved in a pi bond, the lone pair can't be part of the pi system. If the heteroatom isn't involved in a pi bond, then one and only one of its lone pairs can be part of the pi system. So yeah, oxazole is aromatic. It has the right number of pi electrons. And you should do some more, there's tons of examples in your book, you should practice this. We can use the concept of aromaticity to try to to answer some other questions about stability of organic molecules. For example, suddenly I can't draw a 5-membered ring. Okay, close enough. For example, we can compare these two molecules. People have told me that my 7-membered rings resemble somewhat sad robots. Aw. Should we turn that up a little bit? So in any case, which of these two is more acidic and why? Okay, now don't let your brain explode yet. This isn't as hard as you think it is. When analyzing acidity of protons, it's almost always best to draw the conjugate base. So, in fact, previously in 351 in chapter 2, I think for some of you, I suggested that you meditate on the phrase, draw the conjugate base, and sort of repeat that to yourself as a mantra. So let's draw the conjugate base of these two hydrocarbons. Here's one. And here's the other. I think the one on the left looks sort of like not necessarily, maybe like an evil robot alien, whereas the one on the right looks just sort of sad. Okay, so look at those anions. Tell me about this one. Does it check the boxes for aromaticity? Cyclic, Fully conjugated, how many pi electrons? 6, good. So this one is aromatic. How about this one? It would be anti-aromatic, right? It has 8 pi electrons versus 6 pi electrons. So let's go back and use that to answer the question about which is more acidic and why. Which conjugate base is more stable? The aromatic one, right? That's what aromaticity means. So the more stable conjugate base has the more acidic, more reactive acid. Okay? Cyclopentadienyl anion is quite stable. Yeah.
When we were preparing for today, we saw some videos that said that a lone pair could act either in the pi system or not in the pi system, therefore making it non-aromatic instead of anti-aromatic.
Okay, the question is, you've seen some video content, presumably not mine, okay, that said that a lone pair could either be part of the pi system or not, thereby making something either anti-aromatic or not aromatic. I don't exactly know what you're referring to. Lone pairs don't choose anything. So what I think they're referring to is the idea, which is true for molecules also that don't have lone pairs, like these two examples. For anti-aromatic molecules, if they have an option to distort their geometry so that they're not planar and fully conjugated, they can avoid anti-aromaticity. Do you recall a specific example?
It was specifically with like plus and minus charges, but I don't.
Okay. If you find it and think of it, yeah, go ahead.
So if you go down to the example that you were just doing with the lone pair, it was saying that you could choose to like put it down so that it acted as an sp2 at that carbon, or just leave it there so that it's sp3. And his rule was like, if it's sp3, then it's non-aromatic.
Okay. I think what that I think what the content provider is trying to communicate is the idea that, like I've said, some molecules, if they can distort their geometry, they can avoid anti-aromaticity. So if you could make this anion, you might expect this atom, if it can, to tilt out of planarity to avoid being anti-aromatic. That being said, I think that kind of thing is difficult to predict, and for us, it is enough to know that it would be anti-aromatic. Okay, so that's why I've said we're not going to use the issue of planarity per se as a test for whether something's aromatic or anti-aromatic. Understand that if something's aromatic, planarity is sort of a consequence of that. If something's anti-aromatic, it will, if it can, avoid planarity so that it can avoid being fully anti-aromatic. But it's important to recognize that this would be unstable. You see what I'm saying? Like, it's not enough to call this not aromatic, because this is different than just a plain old not aromatic molecule. It's got special instability if it otherwise checked all the other boxes. Okay, others? Yeah.
So for a molecule to be anti-aromatic, it has to be cyclic and planar, you're saying. So like for the example, like your first example where you had the nitrogen, like it has 4N and it's cyclic, but it's not.
Right. So can you help me out? Which example are you talking
Sorry,
about?
like the first one when, sorry, go up a little bit.
Not that?
Yeah, sorry, keep going. Yeah, that one on the left. So like it has.
Right. This one is not fully conjugated. So
that's part of the.
that's yeah, your first two rules are cyclic, fully conjugated, and then pi electrons. If you don't check the box for fully conjugated, the number of pi electrons doesn't matter.
Okay, so it won't be.
It's just plain old not aromatic, yeah. The only way you're anti-aromatic is if you check the first two boxes and you have the wrong number of pi electrons.
Thank you.
Yep. And I think what we're seeing is that some people would tell you, oh, well, cyclooctatetraene is just not aromatic because it distorts its structure so it can avoid being anti-aromatic. I believe that's technically true, but the only reason it distorts its structure is to avoid anti-aromaticity. So I feel like it's important to note that problem with the wrong number of pi electrons. Does that make sense? Okay. We can also ask this question in kind of an interesting way. Which reacts faster in an SN1 reaction? I feel like maybe I'm giving away exam questions at this point, but what the heck? Whoa, suddenly people went to reach for pens. That was kind of fun. Okay. Now he doesn't look sad, he just looks like he feels ridiculous with the chlorine on top. Okay, so which reacts faster in an SN1 reaction? Remember, in an SN1 reaction, the leaving group leaves. And we judge quickness of SN1 reactions by how stable the carbocation intermediate would be. So go ahead and draw the leaving group leaving. And then let's consider these same sort of geometries with cations instead of anions. And I'm going to angle his mouth upward a little bit because, as you can see, the cycloheptatrienyl cation has 6 pi electrons. It's, as we see, cyclic and fully conjugated. It has the right number of pi electrons, so it would be aromatic versus the cyclopentadienyl cation, which would be anti-aromatic. The difference is in the number of pi electrons here, right? The cation tells us we only have 4 pi electrons on the left, but 6 pi electrons on the right. So yeah, you would expect this one to react faster in the SN1 reaction. So we can use concepts of aromaticity to explain reactivity. All right, questions? Okay, so I want to spend maybe 5 or 10 minutes telling you about where the Huckel rule comes from. And I'm trying to hold myself back because there's more detail I could give you that would be cool to know, but it's probably not that useful to you at this stage in an introductory class. So recall when we've talked about molecular orbitals before, you've seen 2 p orbitals added together to form a pi bond and a pi antibonding orbital. Does that sound familiar? And in 351, you talked about conjugation of dienes. You've seen butadiene, 1,3-butadiene like this. And you've seen the system of pi orbitals that comes from 1,3-butadiene before. I can draw some of them. Maybe we don't need to draw all of them. There's a p orbital on carbon 1, on 2, on 3, and on 4. I'm drawing the top lobe of each of those, and then the bottom lobe is below the plane of the page. And they are aligned with each other, and you can mix these 4 p atomic orbitals together to get 4 pi molecular orbitals out, right? And they increase in order of energy based on the number of nodes that they have. You've probably seen the lowest energy orbital basically look like this, where all the p orbitals are lined up together with the same wave function sign, 0 nodes, whereas the next highest energy one has a node in the middle. There's a switch in wave function sign. Is that all looking familiar? Notice that these orbitals obey symmetry rules, which are tied up also in probability, which we don't need to go into. Notice that in the pi1 molecular orbital, that this lowest energy orbital is what we will call mirror symmetric, meaning the wave function sign is identical on carbons 1 and 4 and identical on carbons 2 and 3, whereas the pi2 orbital has what's called mirror anti-symmetry. Notice that the orbital is identical on carbons 1 and 4 except opposite wave function sign. The orbital is identical on 2 and 3 except opposite wave function sign. Okay, so that's all sort of background to remember what's going on. Another useful concept from MO theory, just to review briefly, is that you can tell whether an orbital is a bonding orbital versus an anti-bonding orbital by simply keeping track of the number of times on adjacent atoms the wave function sign is the same. When the wave function sign is the same, we call that a bonding interaction, BI. When the wave function sign is opposite, we call that an anti-bonding interaction. And so if an orbital has more bonding interactions than an anti-bonding interaction, it is a bonding orbital, and you can rank orbitals in energy based on how many bonding interactions they have. For example, this lowest energy mirror symmetric orbital has 3 bonding interactions, whereas the next highest one has has 2 bonding interactions offset by 1 anti-bonding interaction. So we'll call that 1 net bonding interaction. The anti-bonding interaction cancels out one of the bonding interactions. This is just another way really of counting nodes and ranking orbitals in energy. All right. With that in mind, I want to just briefly contrast 1,3,5 hexatriene with benzene. And all we're going to do on this is just consider the lowest energy orbital. Again, think about mixing 6 pi molecular orbitals together, and the lowest energy combination will always be the one where there's no nodes. For simplicity's sake, we're only looking at the top lobe of the orbital. Are we all okay with this? We've got a lobe below the plane of the page. Now we'll do the same for benzene, and the only difference is in 1,3,5 hexatriene, the orbitals are arranged in a line with 2 ends, whereas in benzene, the orbitals are arranged in a cycle with no end. Let's count the number of bonding interactions that you've got in benzene. Sorry, 1,3,5 hexatriene. 5 places where there's no change in wave function sign between atoms. But benzene, because it's cyclic, you have 6 bonding interactions. Okay? That's why the cyclic and fully conjugated matters, and that's where some of the extra stability comes from being cyclic. Benzene is less reactive than 1,3,5 hexatriene, more stable because it has more bonding interactions. That means that lowest energy, this is the pi1 orbital for benzene, is lower in energy than the pi1 orbital for 1,3,5 hexatriene. Okay? So that's one reason. A second reason starts to happen as you consider some of the higher energy orbitals. And to do this, what you've seen before in, say, butadiene is that as you go up in energy, you increase the number of nodes, right? So 0 nodes in the first orbital, 1 node in the second orbital. Let's look now at benzene, and let's try to think of that, and we'll maybe move this here. Let's try to think of what the next orbital in energy would be like. And again, we're going to follow to some extent the pattern that we've seen before. The second orbital has to have 1 node and has to have mirror anti-symmetry. Sort of 2 different ways of saying the same thing. So let's think of a way that we could have 1 node and mirror anti-symmetry. Of course, a simple way would be to put the node in between the first 3 atoms, 1, 2, and 3, and the second 3 atoms, 4, 5, and 6. And maybe it would help us to number the atoms. You can see that 3 and 4 are identical except they're mirror antisymmetric. 2 and 5 are identical except mirror antisymmetric. And 1 and 6 are identical except mirror antisymmetric. Okay? So that's one option. Now, if we were in linear 1, 3, 5 hexatriene, the next orbital would have 2 nodes and so on. But it turns out that because this molecule is cyclic, there is another option for a 1-node orbital that has exactly the same number of bonding interactions. In this case, let's have the node coincide with atoms 5 and 2. The node is going to pass through atoms 5 and 2. Then atoms 1 and 6 are going to be on one side of the node, and atoms 3 and 4 are going to be on the other side of the node. Again, this orbital is going to have 1 node, and it's going to have mirror antisymmetry. And if we count up the number of bonding versus anti-bonding interactions for these 2 orbitals, we're going to get the same number. This orbital pi 2 has 4 bonding interactions offset by 2 anti-bonding interactions for a total of 2 net bonding interactions. Whereas pi 3 has 2 bonding interactions, but no anti-bonding interactions because there are no adjacent atoms with opposite wave function sign. So pi 3 just has 2 bonding interactions. And I'll highlight, 0 anti-bonding interactions. Pi 2 and pi 3 have the same number of nodes, the same overall net bonding interactions. They have the same energy and stability. They are what we call degenerate. So it's almost as though in 1,3,5 hexatriene, which is our linear conjugated system, what ends up happening for benzene is the lowest energy orbital moves lower because it has more bonding interactions. And then the highest energy orbital also moves lower to get to the same position as that pi 2 orbital. So you got 2 orbitals basically moving down in energy. And this is actually the origin of the 4n plus 2 rule, because you can see that for benzene, we would put 2 electrons in this lowest energy orbital. And then if we completely fill pi 2 and pi 3, that's 4 electrons at the same energy level. So in order to fill the bonding orbitals in benzene, we need a pair of lowest energy orbitals and then 2 pairs of higher energy orbitals. This is the +2 of the 4n plus 2 rule, and this is the 4n. Okay? You can look at this all over the place. This should be in your text in a little bit of detail, but this is where the 4n plus 2 rule comes from. Because of cyclicness and conjugation, the pi orbitals will always have one that's lowest in energy, and then beyond that, they will always have degenerate pairs of higher energy bonding orbitals. Okay. So it turns out that scientists or chemists have a mnemonic device for remembering all of this. It's called the Frost circle or the inscribed polygon method. But it turns out that if you draw a circle, and I'm lucky because Notability will draw a lovely circle for me, just like that. And then if you take any cyclic aromatic or cyclic hydrocarbon that you want to determine whether it's aromatic or not, and if you draw that 6-membered ring point down within the circle, every place the 6-membered ring touches the circle is a place, it marks the relative energy of the orbitals, the pi orbitals of that ring, relative to each other. In other words, I've got a lowest energy orbital here, that's pi 1. I have 2 pairs of higher energy orbitals here, pi 2 and pi 3. The midpoint of the circle, or the line that divides the circle in two, is the so-called non-bonding line, or the energy level that distinguishes bonding from anti-bonding orbitals. And then this would predict that in the anti-bonding area, I have 3 other orbitals, pi 4, pi 5, and pi 6, that are all anti-bonding, but pi 4 and pi 4 and pi 5 rather are equal to each other in energy. And then of course, if you want to fill the orbitals up with the available number of pi electrons, there you go, benzene is aromatic because all the bonding orbitals are filled, none of the anti-bonding orbitals are filled. This Frost circle is merely a mnemonic device for helping you out with the Huckel 4n plus 2 rule. For weird reasons, it turns out if you draw your circle perfectly and your polygon perfectly, it is pretty quantitatively predictive. Like the distance between here and here versus here and here really does describe the relative energy differences between this lower energy orbital and these higher energy orbitals. Not sure why it works out that way, kind of cool. But at least as a mnemonic device, this will illustrate for us what the deal is with anti-aromaticity. If I draw a circle again, and then draw a square within that circle, point down, whoops, let's see, now I need a square. All right, that looks vaguely like it maybe was trying to be a square or a diamond. Close enough. Every place the square touches the circle is the location of a pi energy orbital, or a pi molecular orbital. Notice that pi 2 and pi 3 are equal in energy. Also notice that pi 2 and pi 3 are right along the midpoint of the circle, that so-called non-bonding line. Now, go back to cyclobutadiene. It has 4 pi electrons. 2 of those are in the lowest energy orbital. The remaining 2 have to go in those 2 degenerate pi orbitals, following the whatever it's called. Is it the Aufbau principle? You fill each orbital with one electron first, parallel spins. Notice that actually this is the origin of anti-aromaticity. You look at the structure of cyclobutadiene and you think, okay, well, there's at least 2 pi bonds. False. There's not even 2 pi bonds. There's max 1, and the remaining 2 electrons are as though there were no pi bonds at all. They're in non-bonding orbitals, and also that's not supposed to happen. What happened there? The screen went to sleep. Sorry. I think the video was still rolling. Man, lost my steam. Where was I? I was getting worked up about something. You look at cyclobutadiene and there's 2 pi bonds. False, there's not even 2 pi bonds. That's what it was. There's 1 lower energy one, and then you have 2 that are at the non-bonding level, but it's not even a lone pair. They're unpaired electrons. Cyclobutadiene, if it had this cyclic fully conjugated geometry, would react as though it were a diradical. And that's true in general for anti-aromatic compounds. You lack the stability of the bond you think is there, and instead the highest energy pair of electrons is a diradical. Why is that? Well, when the orbital structure is that you have 1 lowest energy pair and then degenerate pairs of 2 orbitals all the way up, and you only have 4 n pi electrons, you're always going to fill the lowest energy one. You're always going to run out and only have 2 electrons for that highest energy degenerate pair. Yeah?
Just I'm just a little confused how a diradical can still have the appearance, like when we draw the structure, it looks like it has 2 pi bonds. Like, could you explain that, how those 2 radicals make it look like that?
I guess your question is, how do you know looking at this that it's a diradical? You don't without the MO theory picture. And this is where sometimes the simple ways we have of drawing structures, Lewis structures, and even with the concept of resonance, fail to capture an important feature of molecules. So yeah, you don't know about this diradical thing unless you know about the Huckel 4n2 versus 4n rule, which you don't know about if you don't understand what the orbitals look like. Yeah?
Will the length of the carbon-carbon bonds be slightly greater than a single bond and slightly lower than a double bond?
Good. You mean these here?
Like all of the bonds, will they be in between a single and double bond?
Well, so for benzene, which is aromatic, yes, the bonds are all the same length, and they are shorter than single bonds, but a little bit longer than double bonds. Because for cyclobutadiene, because anti-aromaticity is so destabilizing, as I said, it will distort its geometry so that it can avoid being planar and fully conjugated. This may be reflected here, perhaps not. Okay, yeah, it actually is. Do you see how it's actually lengthened those pi bonds? That's trying to break up some of the conjugation. And if you look at what the HOMO and LUMO look like, you can see we're no longer dealing with the 4n plus 2 pattern of degenerate orbitals. It's shifted out now so that we avoid that. Anyway, it's an interesting subject, and probably beyond the scope of an introductory OChem class, but yeah. Okay, did I see another hand? I know we've gone long, but this sort of finishes up chapter 19, and I figured it was better to do it all in one chunk than to have a break and then come back and have me try to get up to that. It's not even 2 double bonds point. All right, let's take a break. We'll be back in 5, and then we'll start chapter 20.